Good morning, all of you. Today we will be discussing the static characteristics of an SCR or VA characteristics of an SCR. Static characteristics of an SCR or VA characteristics of an SCR. Now, in order to explain this VA characteristic, we need to be much more familiarized with the three modes of operation. In the previous sessions, like the previous two sessions, we have discussed about the three different operating modes of an SCR. That is reverse blocking mode, forward blocking mode, and forward conduction mode. Okay. To make you much more analyzing the VI characteristics or much more aware about that, let's just see the forward blocking mode. We have an anode, we have a cathode, we have a gate. Okay, so it's a forward blocking mode, so this is the biasing that we are providing. And this voltage, okay, we are now going to analyze two main parameters. Analyze means we are going to consider two main parameters. The first one is the voltage between anode and cathode. We call by the name VA. VA, that is voltage between anode and cathode. Okay, and when the device conducts, there will be a current flowing from anode to cathode, right? There will be a current flow from anode to cathode. And we call that current as IA. That is, there is a voltage when we apply between anode and cathode. If there is a current flowing from anode to cathode, we call that current as IA. So we will be observing these two parameters, that is voltage across the device and current through the device, IA. Okay, voltage across the anode and cathode and current through the device, that is IA. We call that current as anode current. That is a current from anode to cathode. Okay, so assume that initially assume that we are not applying any voltage. That means if the voltage is 0. Obviously, what is the current flowing through the device? When the voltage is 0, what is the current? Current is also equal to 0. Okay. Now, if I am gradually increasing the voltage from 0 volt, I am gradually increasing the voltage. That means if I am gradually increasing the voltage, what happens? Yes, this junction J1 and junction J3 will be forward biased, whereas the junction J2 is reverse biased. That is fine. Okay. So that is true. That means the device is not conducting. But when you apply a small voltage, we have studied that a small leakage current can flow through this. Very small leakage current. Very small value. Okay. So when you gradually increase the applied voltage, your anode current will increase and a very small leakage current will start flowing. But your junction J2 is reverse biased. J1 and J3 are forward biased. Okay. And when you increase the value of the voltage, the leakage current value also increases, right? And when you increase the voltage beyond a certain limit, that means very high value that this device can handle, what will happen? There is the junction J2 also will now conduct. Initially junction J1 and J3 were ready to conduct, but only junction which was blocking was junction J2. But when you apply very high voltage, what happens? Junction J2 also now permits the flow of current. So what happens? An anode current will flow from anode to cathode. Isn't it? A current will flow from anode to cathode, and so we can say that we have turned on that device. We have turned it on. Okay, so when very high voltage is applied, junction J2 also conducts. So the device starts conducting from anode to cathode. That means the current now flowing is the anode current IA. Isn't it? And once the anode current IA flows, we can say that the device is turned on. Okay. So did we apply any gate pulse? No, we didn't apply any gate pulse. Still your device starts conducting. Okay, that is one case. Now let's assume another case. Again the same thing. Initially your assumed and that case is over. We are assuming the another case. Voltage is 0. What happened to the current? Current is also 0. Okay. Now I have gradually increased the voltage. Gradually increase the voltage. What happens? As usual, a small leakage current will flow. A small leakage current will flow. So as I increase the applied voltage, the leakage current also increases. Right? Okay. Now with that very small value of voltage, I have provided gate pulse. Gate pulse. That means gate pulse is flowing, and let the corresponding gate current be Ig. Ig1. Some gate current. So what happens whenever it receives a high, whenever it this like P, N, right? Whenever this P region receives a gate current, what will happen? The junction J2 will be forward bias and the device starts conducting. So when you increase the gate pulse, when the gate pulse is given, gate pulse means I am giving in the form of current, a voltage. With the help of this voltage, a current is flowing through to this, isn't it? So when I give this gate pulse, what will happen? The device will get turned on. When the device turned on, what is the current flowing through it? The current flowing through it is Ia. Okay, that means even with very small voltage, by applying a gate signal or applying a gate current, I can turn on this device. Clear? Now, next second case, I have applied another gate current whose value is less compared to this. Okay, I have applied a new gate current whose value is less compared to the first gate current. So what happens? I need to increase the voltage to make it turn on. Okay, so initially assume that in the first case, when the gate current was Ig1, your voltage was, say, let it be 3 volt. Let it be 1 ampere. These values are not accurate actually. So in the first case, when I have given 1 ampere gate current, with 3 voltage, the device turned on. Okay, but in the second case, I am giving 0.5 ampere. So with 3 volt, will the device get turned on? No, the device will be turned on at some other high voltage compared to this. Now, if I am applying another gate current Ig3 whose value is 0.25 ampere, that means gate current is less. So in this case, will the device get turned on at 4 volt? No, the device will be turned on at some other high value of voltage. Okay, so that means when I increase the value of gate current, I can turn on the device at very low voltage. But if I decrease the value of gate current that I am providing, I can turn on the device at some other high voltage. Am I clear? So this is a relationship between the magnitude of the gate current that I am supplying and magnitude of the applied voltage required to turn on an SCR. See, these values are not correct. I am just explaining this for simplicity. Okay. So with gate current, the device can be turned on at low voltage. Okay. So keeping all these things in mind, we are going to explain the VA characteristics of an SCR. So VI characteristics, rather VAIA characteristics. That means anode voltage, that is voltage between anode and cathode, and anode current flowing from anode to cathode. So this is the axis. So as a name itself, VI chara. So x axis it will be VA, y axis it will be IA, positive, and here it would be minus IA, and here it would be minus VA. Okay, so let's see. Initially when the anode voltage is 0, your current is also 0. No issue. Now when you gradually increase the voltage, what will happen to this is a current is increasing in this direction, voltage is increasing in this direction. So when you gradually increase the voltage, your current value is also increasing gradually like this, isn't it? Okay, when you increase the voltage, the current is gradually increasing, very small leakage current. This is very small leakage current. Leakage current. Okay. Now, when it reaches a value of voltage, we call by the name VBO. VBO means break over voltage. When it reaches a value VBO, what happens? This is the highest value, and when once it reaches VBO, what will happen? Junction J2 also starts conducting, and your current increases gradually. And once a device starts conducting, let this be the anode and let this be the cathode. Once a device starts conducting, that means it is connected like this, isn't it? Once a device starts conducting, what is the voltage across that device? Voltage across that device will be very less or very small value, isn't it? And what about the current? Current will be very high, isn't it? Current will be very high. So initially the voltage across the SCR was VBO, but at this point what happens? The current increases or the device starts conducting. Once the device starts conducting, what will happen to the voltage across the device? It would become very small. Let this be that voltage. Okay, so now the voltage would be like this much, only this much. Initially it was this much. At this point the device starts conducting. Once a device starts conduct, the voltage across the device reduces like this. So, and your current will be, so this was your current, right? This was your current. And from here onwards, the current starts increasing like this. Okay? And this voltage is called on stage voltage drop. This is on stage voltage drop. So, here when the voltage was 0, current was 0. When the applied voltage increases, the current also starts increasing. And when the voltage reaches a maximum value, that is a breakover voltage, the device conducts. Once the device conducts, then the voltage shifts from high value to very low value. And from here onwards, the current will start increasing. Okay, current starts increasing. So, this area, this area, right? What mode is this area? It is forward biased. Is it conducting? No. So this mode is actually forward blocking mode. And what about this area? It is a forward biased mode and the device is conducting. So this mode is called forward conduction mode. Okay. So far we have discussed only about the voltage. We didn't mention anything about the gate. Now you just remember what we have discussed a few minutes before. Gate current, we have considered gate current, isn't it? When the gate current reaches, we had the gate currents what? IG1, IG2 and IG3. And your IG1 was higher compared to IG2, which was higher compared to IG3. So if I am applying, when you increase the voltage and if I am applying a gate pulse, what will happen? The device will get turned on at some point like this. Isn't it? At this point the device might get turned on. And if it is IG2, the device will get turned on at some other point with a very high voltage. And when you are applying a new gate pulse IG3, device might have turned on at some other voltage, isn't it? So this would be the graph if IG1 is applied. This would be the graph if IG2 is applied. This would be the graph if IG3 is applied. And this would be the graph if no gate pulse is applied. Okay. So this corresponds to IG1. This corresponds to IG2. This corresponds to IG3. Okay. So that is about the forward condition. Now let's see what will happen in the reverse. Reverse condition is quite easy because you know already what is the VI of a diode and all. Okay. So here in the reverse condition, when you are applying 0 voltage, the current is also 0. When you are applying reverse current, what happens? the leakage current increases gradually, right? And when it reaches a voltage which we call it as VBR, or you might be knowing this as reverse breakdown voltage. What will happen at this very high reverse voltage is applied to this particular device, junctions will get breakdown and the device will get damaged, right? So, and under this voltage, what will happen? The device will get damaged and a very high current flows through this device, reverse current. So that's it. So here when you apply a reverse voltage and then gradually increase the reverse voltage, and when the reverse voltage becomes greater, equal to or greater than VBR, that is reverse breakdown voltage, the junctions get damaged, junctions breakdowns occur and the device will get damaged, very high current flows through this. It is not conducting, it is breakdown. And so this area, we call it by the name reverse blocking region. Reverse blocking region. Okay, so that is happening. This is the forward blocking mode, this corresponds to forward conduction mode, and this corresponds to reverse blocking mode. Now at this point we need to understand one more concept, that is regarding latching current and holding current. We need to understand what is latching current and holding current. Okay, so here when did this SCR turned on? Whenever it reaches VBO or IG3, IG2, whatever it may be. So whenever the anode current, this is the anode current axis, right? Whenever the anode current of an SCR becomes equal to a particular value, okay, when the voltage increases, the anode current also gradually increases, right? So whenever this anode current increases and reaches a value equal to latching current, then the device will be turned on. Clear? So we have mentioned that VBO, the device will get turned on, right? Like something like that, isn't it? So what is happening at VBO, the anode current becomes equal to latching current. Okay, so whenever the anode current increases and becomes equal to latching current, the device will get turned on. Only when the current reaches latching current, the device will be turned on. Okay, but if you decrease the anode current, and when they decrease the anode current below latching current, the device will not be turned off. Okay, so assume that your latching current is 100 ampere. This is not an exact value. Assume the latching current is 100 ampere. So when you give the biasing and all, when the current increases and reaches 100 ampere, the device will be turned on. Once the device is turned on, the current starts increasing and reaches, say, 1200 ampere. But if I reduce this current, and when the current goes below this 100 ampere, say let it be 99 ampere, device will not be turned off. Okay, but the device will be turned off when it go beyond a particular value, which we call by the name holding current. Okay, so whenever the current decreases and it goes below this holding current, the SCR will be turned off. Okay, and from the graph itself, it is clear that your latching current is greater than the holding current. Latching current is greater than holding current. So here, what is latching current? Latching current is the minimum anode current required to turn on the SCR. And holding current is the minimum anode current required to maintain conduction or to maintain on stage. Or holding current is the minimum anode current below which the SCR will be turned off, and your latching current is always greater than holding current. So this is the VA characteristics of an SCR. The parameters which is to be made much more clear is 1. VBO, forward breakover voltage. What is forward breakover voltage? It is the voltage at which the SCR gets turned on even without gate pulse, or it is a maximum value of forward voltage. Okay, and VBR is the break down voltage. That means it is in the reverse direction. So it is the maximum value of anode current in the reverse direction beyond which the SCR will get damaged. Okay, and what is latching current and holding current? Latching current is the minimum anode current required to turn on an SCR. Holding current is the minimum anode current required to maintain conduction. And this represents the so whenever it is asked for an exam, you need to draw all these and mark latching current, holding current, VBO, VBR, which is the forward blocking mode, forward conduction mode, reverse blocking mode, on stage voltage drop, IG1, IG2, IG3, and IG1 is greater compared to IG2, which is greater compared to IG3. So this is the VI characteristics. V is the voltage across anode and cathode, and I is the current from anode to cathode, or the static characteristic of an SCR, silicon controlled rectifier. Thank you.